Okay, everyone, welcome to section 2 point something. Now you might be wondering, what the heck does 2 point something mean? Well, here's the deal. This section is going to cover the idea of determinants of a matrix. Okay. Now, determinants of a matrix are going to be a math thing that we're going to be using to solve systems of equations. Now, we have already looked at several techniques for solving systems of equations. This is just going to be another technique for solving systems of equations. The reason I'm calling it section 2 point something is it's not in our book. It is not a section as in our book, but it's required for this course, and because it's for solving systems of equations, it goes in this chapter, hence 2 point something. Okay? All right, so what are our objectives? Well, we're going to define what this determinant is. We're going to define how to find it, and then we're going to use that determinant to solve some systems. Pretty short section, maybe 1 or 2 videos total. Okay? All right, so first off, what is a determinant of a matrix? Well, determinants of matrices have a lot of applications, but most of those applications are going to be in higher mathematics. And what I mean by that is courses well beyond where we're currently at. So we're talking like 3 and 4 and 500 level math classes. Right? What we're going to be using them for is we're going to be using them to solve, or as a step in solving, linear systems. Okay? So our job is less about being able to define necessarily what a determinant is, but more about how to calculate one and then what to do with it once we calculate it. Sorry. So here's our definition. It says that any square matrix that has an inverse has a non-zero determinant. So when you read that, there's a lot to unpack there. But first off, determinants only exist for square matrices. Determinants only exist if your matrix has an inverse, and determinants will always be non-zero. That means that they can be positive or negative, but they can't be zero. Okay? The downside to it is because our matrices have to be square, and they also have to have an inverse, then all of the same restrictions that existed last section in matrix algebra exist here. That is, that this technique that we're going to look at here can only be used on systems that have the same number of equations as variables and systems that have a unique solution. If you have a system that has no solution or infinitely many solutions, remember when we parameterize stuff, that's infinitely many, you can't use this technique to solve them. Right? That's not to say that it's not a useful technique. It's just simply to say that it has limitations. All right, so the determinant of a matrix is going to be a non-zero number. It only exists if your matrix is square and has an inverse. So that means that there is the possibility that someone could ask you for a determinant and your answer could be there isn't one. Okay. All right, so what are we going to do with them? Well, we're going to find them, and then we're going to use them to solve systems of equations. All right. As with most things in mathematics, we have some notation for the determinant of a matrix. So if you have a matrix and its name is, say, matrix A with the square brackets around it, we would either say the det of A like that for the determinant, or sometimes you'll just say det of A and leave off the parentheses, or sometimes you'll say, and it looks like absolute value bars, and technically you wouldn't be wrong if you said they were absolute value bars because it is the same notation. The difference is when you use absolute value, the thing that you put inside of those absolute value bars will always be either a number or a single variable or something like that. Whereas here, since we're putting a matrix, in this case matrix A, inside of those absolute value bars, then we know that it doesn't mean absolute value, it means determinant. We recycle notation. Right? If your matrix is written out longhand, there's a typo there. That should say A, B, C, D. Then the determinant would be written with those straight bars on both sides. It looks like absolute value. Okay? All right, so let's go ahead and find one. Let's just jump right into it. Our definition here says to find the determinant of a 2 by 2 matrix, A, B, C, D, you take A times D minus B times C. A great way to remember it is we go this way and then we subtract back. We multiply down the main diagonal and then we subtract back that other diagonal. And that's our determinant. Let's take a look at a couple of examples. Here I have the matrix 1, 5, negative 1, 6. My job is to find the determinant. So I'm going to use proper notation, 1, 5, negative 1, 6. And I will say the determinant of this is going to be that 1 times that 6 minus that 5 times that negative 1. 1 times 6 is 6. 5 times negative 1 is negative 5, but we're subtracting, so that makes it positive 5, and I get 11. Now, I have no clue what 11 means yet, but I know that the determinant of that matrix is 11. What it means and what we'll use it for will show up here in a little bit. All right, next matrix. 3, negative 6, 7, 9. The determinant of the matrix 3, negative 6, 7, 9. Oops. Is that 3 times that 9 minus that negative 6 times that 7. 3 times 9 is 27. 6 times 7 is 42, but it's negative, but it's another negative because we're subtracting it, so plus 42. 42 and 27 is what? 60, 69. And so the determinant of the matrix 3, negative 6, 7, 9 is 69. And I can just keep doing this for as many as they throw at me. What's the determinant of 1, 8, 12, negative 4? Well, that's going to be 1 times negative 4 minus 8 times 12. 1 times negative 4 is negative 4. 8 times 12 is what? 96, so negative 96. And I've got negative 100. There's my determinant. And I could keep doing this forever and ever and ever and ever because it's not that hard, right? All right, so what would a matrix have to look like for it to not have a determinant? Well, the only time that a matrix wouldn't have a determinant is if when you did this math for the matrix A, B, C, D, if you did the math AD minus BC and got 0, when you did that math, that would tell you that the matrix has no determinant because the determinant must be a non-zero number. It can be positive, it can be negative, but it can't be 0. So if I did the math and got 0, I wouldn't write down that the determinant was 0. I would say that this matrix has no determinant. Because the determinant of 0 technically means it doesn't have a determinant. A determinant can't be 0. Right? Something else to keep in mind. While every example that we did here worked out to a nice whole number for the determinant, if the entries of your matrix were fractions or decimals, then you could absolutely get a determinant here, here, or here that was a fraction or a decimal, and that would be okay. All right, so 2 by 2 matrices, if my job is to find the determinant, I've got a formula. What if a matrix is bigger? Well, for matrices larger than a 2 by 2, there are a bunch of different techniques depending on what you're looking at, but the most common technique is to reduce larger matrices down to the sum of several 2 by 2 matrix determinants. Right? Now, the process involves using something called cofactors and minors. Okay? Cofactors are entries from the matrix we started with, and the minors are a reduced matrix that we create using the cofactors. It absolutely will make more sense when we do an example. All right, so I am going to find the determinant of this following matrix, of this 3 by 3 matrix. Now, in order to find the determinant of a 3 by 3 matrix, I need to pick any row or any column of this matrix, and that row or that column will give me my cofactors for the matrix. So just to keep things simple, I am going to pick row number 1. Now, row number 1 will give me the following. It will give me that the determinant of 1, 4, 7, 3, 0, 5, negative 1, 9, 11 is 1 times, and where did that 1 come from? That 1 is the first entry there. And then what I'll do is I will ignore the row and the column for that cofactor and then just use that resulting matrix. So do you see that little 2 by 2 matrix right there? That's going to be the one that I will find the determinant of. And then I'm going to subtract. Why subtract? Because the second entry in that row, you subtract. So now my second entry is the 4, so I'll ignore that row and that column. Okay. And so it's going to be minus 4 times the determinant of the matrix 3, 5, negative 1, 11. Those resulting, or those leftover entries after I have that ignore row and ignore column. Okay. And then I'll do addition. Why addition? Well, because the pattern is positive, negative, positive. And so then the last cofactor in that row is going to be that 7 there. So it's going to be plus 7 times, and when I ignore that row and that column, what's the matrix that's left? 3, 0, negative 1, 9. And now I'm just going to do this math right here. Okay? So I have 1 times the determinant, 0 times 11 minus 5 times 9, minus 4 times the determinant, 3 times 11 minus 5 times negative 1, plus 7 times the determinant, 3 times 9 minus 0 times negative 1. Okay. That's 0. This is negative 45, so I get negative 45 for my first entry. That's 33. That's 5, so plus 5. 33 plus 5 is what? 33 plus 5 is 38. So minus 4 times 38. And then down here, that goes away. 3 times 9 is 27, plus 7 times 27. Negative 45 minus 4 times 38. 4 times 38, I'm going to need a calculator for that. Let's see. 4 times 38 gives me 152, so minus 152, plus 7 times 27, that's 189. So I have a negative 45 minus 152 plus 189, and I get negative 8. And so my matrix has a determinant of negative 8. So I know what at least one person is asking. When you started, you said you could pick any row or any column. What if we had picked a different row? Will we have gotten a different answer? Okay, so hold on to negative 8. In fact, I'm going to write it over here to the side so we don't forget. Okay, what if we had chosen a different row? So let's get rid of all of this hot mess. In fact, let me do it a different way so it's easier to get rid of it. Okay, what if we had chosen the second row? So let me put a little arrow there so we know we're working on the second row. Well, it's going to start out similarly, but because we're in the second row, the pattern isn't plus, minus, plus, it's minus, plus, minus. So it's going to be negative 3 times the determinant. Now when I get rid of that row and that column, I'm looking at 4, 7, 9, 11. And then plus 0. And when I get rid of that row and that column, times the determinant of the matrix, 1, 7, negative 1, 11. And then 5, so minus 5, and 1, 4, negative 1, 9. So then I've got negative 3 times 44 minus 63 plus 0 minus 5 times, let's see what's that. That's going to be 9 plus 4. 44 minus 63, I'm going to grab my calculator. 44 minus 63 is negative 19. So I have negative 3 times negative 19 minus 5 times 13. Negative 3 times negative 19 is going to give me a positive 57. 5 times 13 is 65, so minus 65, which gives me, I believe that's a negative 8 again. Oh, I know what you're thinking. Can we please do it again? Actually, you could. You could continue doing this for any row and any column in this entire matrix as long as you remember the pattern. Now, the simplest way is to just always use that first row, and then you don't have to worry about it. The pattern will be positive, negative, positive for your cofactors, and then your minors will just be those expansion matrices. And no matter how you do it, you will always end up with the matrix value of the determinant being negative 8. Now, the other thing you might want to think about is, did the good people at TI expect that I would want to do this? And did they help me out with this? And so let's bring up the calculator. So I'll pause this and come back when it's up and running. All right, so I'm back and I got my calculator up. So what I want to do is I want to take this matrix, put that matrix into my calculator. So I'm going to go to that matrix menu. I'm going to go over to edit, and this matrix is a 3 by 3 matrix. The entries are 1, 4, 7, 3, 0, 5, negative 1, 9, 11. There's my matrix, so I'll quit out of there. Back to my matrix menu, over to math, and look at option number 1 there, the determinant. The determinant of which matrix? Of matrix A. And what do I get? Negative 8. Or do it by hand. Totally up to you. Okay? Either way, same deal. We're at about 17.5 minutes right now, so I'm going to end this video here. Right? So by the end of this video, here's what I'm hoping. You could find the determinant of a 2 by 2 or a 3 by 3 matrix by hand, or anything else using the calculator. All right, I'll see you back for part 2 where we'll actually do something with these determinants. All right, see you then.